We have Ed Felten, co-founder and chief scientist of Offchain Labs, a company behind Arbitrum. He's going to talk about Stylus, unifying the EVM and WASM Arbitrum. So now let's welcome him.
Thanks. Good morning, everyone. I want to talk about Stylus, which is an upgrade coming soon to an Arbitrum chain near you. So first, let me tell you what Stylus does, or what we're trying to accomplish with Stylus. We're trying to onboard many more developers into the Ethereum-compatible space. We're trying to provide an execution environment which, without giving up EVM compatibility or full composability, gives you more than 10x performance improvement over EVM alone. We want to open up new use cases, and it's coming out very soon. Okay, so the basic motivation here is that in order to scale the Ethereum world, to be able to support the next billion users, as my co-founder Stephen Goldfeder likes to say, if we want to onboard the next billion users, we need to first onboard the next million developers. And if you look at how many developers there are in the world of Solidity or Viper, or basically EVM-targeted languages, you're talking about tens of thousands, whereas languages like Rust or C++, you're talking about millions to tens of millions. And so what we want to do is understand how can we bring those millions to tens of millions more developers into the Ethereum-compatible space without giving up the things that we like, including full composability. So right now we have this kind of divided house. You choose a chain, and in choosing a chain, you're choosing, are you living in the EVM Solidity Viper world, or are you living in the other world where you might use Berkeley Packet Filter or WASM as your execution engine, and then languages like Rust, C, or C++. What we really want to do is have them all at the same time and have it in a fully composable way, meaning that not that there is a separate chain for each one, or not even that there's a separate sort of component on each chain, but that you have full interoperation, full composability, even within the same transaction, between smart contracts that are written in the EVM style and smart contracts that are built in the Rust style. And we want to do this on a layer 2, so we need to do all the things that you can do, that you need to do to make it work properly in an optimistic rollup. Okay, so that's Stylus. Basically, this is the next generation programming environment for Arbitrum chains. Here is a little snippet of code. Basically, as you can see, this is Rust code, standard Rust code. It has the hash Arbitrum directive on the top, and that's essentially a directive to the compiler that says things about how to compile it and which libraries to include, what kind of wrappers to put around it, and so on. But this is basically the idea. We want to be able to program in that way. And the vision of this is one chain supporting multiple languages, fully composable, meaning that if a user is interacting with the smart contract, they can't even tell which kind it is, except through things like performance and cost, and that they can call back and forth and interoperate fully within the same transaction. And of course, we want all of the ABIs to work as they're expected. So we call this, it's not a new L2, it's an enhancement to the same chain. And we call this general approach EVM+. We're not taking away what the Ethereum virtual machine provides, but we're just adding a new way to write a smart contract that's fully composable. Okay, so how do we actually do that? I want to spend most of my time talking about how we do it. The first thing is that we do it by having two virtual machines that run together and are fully composable. So if you write in Rust, C, or C++, you can compile to WASM using, say, an LLVM toolchain, or you can write in Solidity or Viper or anything else that generates EVM, and then your code will run on the EVM in the EVM. But importantly, these two VMs are composable and composed with each other, so that there's a single state trie, which is in the exact data structure that Ethereum uses, a single database that they live in, again, unchanged from how it works in Ethereum, and a single state transition function, which is the basic function in a system like this, which takes in a group of transactions and produces the next block. So there's nothing really like it out there that we know of. Okay, so what does this give you? First of all, it's faster. The runtime is faster. Why is the runtime faster? Well, WASM runtimes are faster than EVM runtimes. And they're faster for basically two reasons. One is WASM as an instruction set architecture is more efficient than EVM. You can start with things like the fact that in EVM, the basic data type is 256 bits, whereas in WASM, it's a more practical 64-bit. So as an example, also because WASM has a much larger user base, because it has better tools, and because more engineering effort has gone into building efficient, secure WASM runtimes, the runtimes are just inherently faster by nature. So not only do we benefit by bringing in developers to build on top of it, but we benefit by bringing in all the work that's been done in the WASM community to build fast and secure runtimes. So you get different results, of course, depending on which computation you're doing. But as an example, if you run the Keccak hash function in pure Solidity versus, and then compiled into EVM versus pure Rust compiled into WASM, it's a 73x performance difference. And that means the same computation uses 73x less gas. So this enables new kinds of use cases that weren't possible with EVM alone. For example, if you want some cryptographic primitive, which is not supported already by, it's not one of the few supported already by an EVM Ethereum precompile, and it's too expensive to do on Ethereum via EVM, you can write it in Stylus. And not only can you implement that primitive yourself, but you can take an existing battle-tested library and compile it into your application. So we get the benefit of all of the work, all of the optimization, and work on properties, on important properties of cryptography that has already been put into these libraries. And that, of course, opens up all kinds of applications, new kinds of things. If you want to build some kind of ZK proving thing on top, that's great. You can build the primitives that you need in order to do it. Don't have the group or curve that you need. Just take a C++ or Rust library that implements it, and it will run on an EVM chain. Lots of interesting uses for gaming, interesting uses for AI models. If you want to evaluate a model on some data, this is going to run much more efficiently if it is implemented using Stylus as opposed to trying to do it in EVM. This is also actually interesting for doing research on potential L1 Ethereum precompiles. If you have some precompile in mind, you want to understand how it would run, how people would use it. If it were implemented in native code and built into Ethereum, you can get something pretty close to that by writing it in Rust or C++ and running it on Stylus. So you can prototype L1 precompiles that you're considering. The need for new precompiles on a chain that is Stylus-enabled is much less, because instead of someone needing a precompile to do, let's say, the cryptographic primitive they want, it's already supported. They already have the ability to write it. Okay, so let me dig a little bit more into the technical details of how this works. In order to do this, we need to make sure that we don't break any of the properties that Ethereum already provides for running contracts, which are, of course, untrusted user code. One of the things that we need to support is gas metering. We need to do gas metering in a way that's equivalent to Ethereum, or that is compatible with Ethereum, meaning that the gas that we charge to a contract is actually commensurate to the resources that it uses. So, for example, we need to provide metering of the execution gas of programs. So how do we do that? Well, so first, here we really take advantage of the fact that WASM is a structured and type-safe way of expressing programs. So it's very easy, having validated that a WASM program is correct WASM, which, by the way, we can do on-chain via a precompile. We can then easily divide that WASM code supplied by a user into basic blocks, right? A basic block being just a sequence of instructions that has no branches in or out within the basic block. We can then put in payment and metering code before each one. So, for example, if you look at the My laser's not working. Okay, if you look up at the top box here, the instructions in the basic block, because there's no jumps in or out, and because WASM instructions are simple, we can just statically add up how much computation is happening, how much gas. We actually have to use fractional Ethereum gas, because this is a lot faster. Figure out how much gas does that basic block take, and then we inject code at the beginning of the basic block that first checks to make sure there's enough gas left, and then if there is, subtracts the gas that will be used by this basic block. Because we can identify basic blocks easily, because WASM it has the type safety and structure guarantees that it has, this is easy to do. Also, type safety guarantees that we can inject this gas variable and make sure that the user code doesn't touch this gas variable. If the user code was already validity checked before we did this injection, we know that it can't touch any variables that didn't exist when it was safety checked. And so it's very easy. We just add one more variable to each function that keeps track of this gas, pass it in or out in the appropriate ways. We can inject that code safely, and all of this can be done on-chain via a precompile. So this is efficient. It runs efficiently. It's not operation by operation. It's done once. So first you deploy your Stylus program, and then there's a step you have to do one time to activate it. And when you activate the Stylus program, it takes the WASM code that you provided, and it does this instrumentation step, adds instrumentation, so that it can be run safely with things like gas metering. Okay, so why use WASM and not some other instruction set like MIPS or RISC-V? Basically, these other instruction sets are unstructured, and they don't have the type safety and structure guarantees that WASM gives you. It's not easy to statically analyze a program in one of these other architectures and make sure it's safe and make sure it doesn't try to mess with the instrumentation that we're going to try to add. It's also much more difficult to sandbox those, so it's more difficult to run them within the same executable, so it's hard to compose those virtual machines in a way that's going to be efficient. There's also a lack of tooling generally for using those things. WASM has excellent tooling for this. WASM was designed as a structured and safe way to run untrusted code, and we really take advantage of that in this architecture. All right, let's talk a little bit more about instrumentation. Another thing we need to do is check for stack depth to make sure that programs don't overrun the stack depth, just like Ethereum does. There's an analogous thing in Ethereum. So again, we can do the same kind of thing. We can add instrumentation. Just like gas checking, now we're checking stack depth. Again, because of the structure of WASM, we can statically determine how much stack space each function is using at the time of this instrumentation, and we can inject code that does the appropriate checking to make sure that each function will not overrun the available stack space so that we allow it to have for performance safety, and then to deduct that at the entrance point to the function, and then add back in at exit from the function the stack space that that function is now returning. And so we can give guarantees like you're not overrunning the stack, again, via this type of instrumentation. So we add a check at the top of the function. We give the space back at every exit. It's very easy to figure out where the exits are, again, because of the structure of WASM. And so we can bound the size of stack frames pretty easily and the size of the stack used by a program. So we need to think about these kinds of safety guarantees. And the way that Ethereum does these things is actually a good guide, because Ethereum already has checks for a lot of the things that we need to check here. Point is, we can inject checking code so that it runs efficiently. Okay, let me talk about fraud proofs. Of course, we would not ever release a product or even a test net that didn't have fully working fraud proofs. That's table stakes if you're in this business. Okay, so we, of course, prove fraud over the user execution. On the top, you see how it works in the currently deployed Arbitrum Nitro stack, that we fraud prove over the execution of the trusted Nitro code. That is the state transition function that is published and defines the semantics of the chain, right? And so we have just the execution of that trusted Nitro code in the currently deployed Arbitrum system, and so we fraud prove over that. But in a world with Stylus programs, Stylus contracts, we have interspersed with the execution of that trusted Nitro code the execution of some of this untrusted but instrumented user code. And so you may have some nitro execution on the bottom here, which then, and then you have a, let's say there's a transaction that calls into code in user contract 1, and that in turn may call code in user contract 2, and then it may return to nitro and et cetera. We need to be able to fraud proof over these interleaved computations, which include code that was untrusted, that is not built by us and not statically known at the time that we launched the chain, but of course has been instrumented. Okay, so what do we need to watch out for here? First of all, of course, we need to bound the execution time. We can never call into user code unless we know that it will give us the CPU back within a fixed amount of time, and the gas metering does that. The gas metering where we inject instrumentation makes sure, among other things, that this untrusted code will give us the CPU back in time. And in fact, that not only in time, but that it will actually be charged for and has the funds to pay for any the gas that corresponds to the computation that it's used. So if a user program just keeps running and running and running, eventually that instrumentation code will say you're out of gas, we're going to generate a fault, and that will give control back to the nitro code. So we don't need to worry about that. Similarly, if there is an error, let's say a divide by 0 inside of that untrusted code, we need to make sure the right thing happens. We can't just have the whole VM or the whole state transition function just fault. So we need to catch that, and we need to properly transition back into the controlled code. We have to take care with that. And what does that mean? That means first that we need to put a small wrapper around each one of these pieces of code, which is able to catch the fault, and WASM virtual machines are good at this because they're designed for running untrusted user code that could do all kinds of crazy erroneous stuff. We need to have that wrapper, and also we need to do a little bit of extra instrumentation. Okay, so with all of that stuff in place, when we need to do a fraud proof, when we need to have a dispute, it works the same way that it does today on Arbitrum. You can first bisect over the execution trace down to a single specific instruction where Alice and Bob or multiple people disagree about what the outcome of that instruction is, and then you can fraud proof over that instruction. Because the Arbitrum stack already uses WASM in its fraud proof system, we don't need to add any extra capabilities to do that. We need to do only a little bit of enhancement to the WASM proving engine to handle some error corner cases. But it's essentially no different from the fraud proving mechanism we already have once we've taken care of those other details. So on an error in the execution, we're going to jump back one level, but that jumping back happens through provable WASM execution, and we're able to take care of that inside the Arbitrum WASM execution model. The WASM sandbox really helps us here. So if a user program divides by 0, it's okay. Control will be vectored back into the calling program in a way that's consistent with the EVM execution model. So this will work in the same correct way, whether it's erroring and faulting back into WASM code, Stylus code, or legacy EVM code. So where are we on this? Well, it's fully implemented, including the fraud proofs, and it's undergoing internal testing. We will have a DevNet out very soon, and I mean that very soon. I'm not going to tell you when, but I would be happy to take any questions about what we're doing. Thanks. Dan. Yes. Yeah, WASM can call EVM, EVM can call WASM. And essentially, one way to think about this is that in the EVM model, you have what amount to call frames, where you have effectively a stack of execution environments. So whenever one contract calls another, it's a cross-contract call, and sort of logically in the EVM execution model, there's a thing that's kind of like a stack frame that is created, right? And so when the execution of one of these completes, it goes back into the previous one. In a way, it's like a system call, and in a way, it's like a function call. But essentially, it works like that there is a stack of execution frames, if you will, that represent the execution within one contract. And you can have interleaved EVM and WASM activations on this activation stack. So it works as you would hope in that respect. And that's really important, right? We want these things to be first-class citizens on the chain so that people can use them as if they were regular contracts. In fact, programmers who invoke one of these don't need to know which way it's implemented. Just go here.
So if you call a function from WASM and then return, how do you know that the WASM type system is still safe?
So, as on Ethereum, cross-contract calls go through an ABI where there's call data that's passed across, and there's return data that comes back. So it's the same kind of model as on Ethereum. It's the same way that you know. So the data that gets passed out in one of these cross-contract calls is serialized into a buffer, and the data that comes back is serialized into a buffer. And just like on EVM, when you call some foreign contract, right, it can pass you back any garbage you want, but you need to have the sandboxing so that it can't mess with the state of the caller, right? So each one of these execution frames, if you will, has its own separate space, and they can't trounce each other's space. The only interaction between them is by these cross-contract calls, which happen by passing a buffer of serialized arguments and then getting back a buffer of serialized return data. And of course, you need to be skeptical of the call data that you receive in and the return data that you receive back, but it works the same way.
You're saying that the WebAssembly type system used the values going in and out just as an array of bytes?
Just as an array of bytes, yeah. And of course, there's tooling to help you serialize and deserialize. And you can serialize and deserialize either by using the type of framework that Rust programmers are used to, or there's tooling support for serializing and deserializing to the EVM Solidity ABI, right? But of course, right, just like in a cross EVM call, the data that you get back as return data could be garbage. The only thing you're guaranteed is it definitely is within a buffer of a certain size. Yes? Oh, sorry, yes. The question is, when a WASM program gets a call or a return from a call, how does it know about type safety? Right? And the answer basically is everything is serialized. Everything that goes cross-contract is serialized into arrays of bytes of fixed limited size. Yep.
Great, thanks. So first of all, really exciting work to see, and great to see Arbitrum taking the lead on this kind of VM work. I did have a question that some of the things that you guys are looking at, I feel like I followed the Near Protocol and Ilya and those guys a while back, doing WASM, doing good gas kind of block-based
Yes.
EVM interpreters, even
Yeah.
others. Has there been any collaboration between those teams? They're also doing blockchain.
Yeah. Question is this: has there been collaboration with other teams building, such as Near building WASM EVM? We've looked really closely at what they have done. It's not quite a match for what we want and need to do. So we've certainly learned from what those teams have done, but there has not been collaboration at the code level.
Okay, and since I'm more familiar, I've looked at over time, the work and the progress they've done. What's the key differentiation point of some of the extra improvements that you guys have made?
So one of the things that we are really focused on is backward compatibility with the EVM space. To have complete backward compatibility so that the data structures are the same, and so that we have sort of the full interoperability. We also need something which is susceptible to the kind of fraud proving that optimistic rollups need to do. And differences in consensus protocol actually do, in some respects, bleed into implementation decisions here. I think the constraints of the VM that we are in are one of the, and consensus are the considerations. I'd be happy to, I'm not the best person on our team to answer this question because I'm not the one who has studied the work that those protocols have done, but certainly I'd be happy to put you in touch with the folks who have.
Like I said, it's very exciting.
Thanks, thanks.
Especially even interesting in like your later line applications.
Thanks. Up here.
I'm not familiar with the fraud proofs, but like, why is this bisection protocol? Like, what is unique about it?
What is unique about the bisection protocol? Yeah, let me talk a little bit about that. So the idea is, and this is an idea that actually goes back to the research community 12 years ago, and then has been built out in the blockchain space since then. The idea is, if you have a dispute between, let's say, Alice and Bob about the result of 1 million steps of computation, right? They agree on the starting state, they disagree on the end state. How can you resolve that dispute and identify one of the two parties as a liar efficiently? And the answer is, first you ask Alice and Bob to say what the state is halfway through, right? And then if they agree there, great. Now you have a dispute about the last 500,000 instructions. If they disagree about the midpoint, you have a dispute about the first 500,000 instructions. Either way, you've divided the dispute in half. Keep doing that after a logarithmic number of rounds. You have a dispute about one instruction, which is trivial to resolve. That's the bisection idea. And that is core to how fraud proofs work in essentially any optimistic rollup that has them. Yes?
What are the limitations of WASM that you might have found, and such as perhaps maybe it's hard to use garbage-collected languages like Go?
Mm-hmm. Sure. Yeah, what are the limitations of WASM is the question. Is it hard to use garbage-collected languages like Go? And the answer is yes, in general. If you're in a world with gas accounting, garbage collection is going to be painful, right? You can, because of the nature of execution in this EVM model, right, where a transaction has some memory that it uses, which is then discarded at the end of the transaction, you tend to operate in an execution model where you just allocate during execution, because at the end of your transaction, all of that memory is going to go away. And then you have storage, which is more sort of roughly file system-like, right, which is managed very carefully because it's quite expensive in the overall scheme of things. So execution tends to go that way. I think if I were to try to build a Go, say a Go mechanism for running on top of Stylus, which would be a fun thing to do, I would try to do it in such a way that we never did garbage collection. We just allocated during the execution of one transaction and then threw it all away at the end. That's what you have right now. Excellent. Okay. Yes? Will there be, yeah, so the question is, will there be 2 runtimes? So I would say, the way I would say it is that there is a single runtime that integrates together an EVM runtime and a WASM runtime. Because WASM runtimes are available as libraries, you can in fact just compile a WASM runtime into the Arbitrum node. And so you won't have to run 2 separate pieces of software. It'll still be a single integrated, let's say, node software or validator software. And so from the standpoint of someone who is running a node or running Arbitrum infrastructure, it'll be essentially the same model. But obviously, there'll be more going on inside of that node. But that integration is key to the model, that we don't want to double or more than double the complexity of running infrastructure. Thanks. Okay, I see I'm out of time. Thank you very much.